Welcome to the UGC lecture series. We are going to talk about sorting again. In sorting, in this lecture, we are going to talk about the concepts of sorting of all the algorithms. We are not going to look into the detailed steps of the algorithm, but what we are trying to explain here would be the concepts of each algorithm based on what we have already spoken about the whether it is an exchange sort or a comparison sort or a non-comparison sort and so on. So, we are going to look further into the details of the different sorting algorithms. In comparison sort itself, we had brute force, we had decrease and conquer, divide and conquer and so on. So, we are going to look at those in detail. Okay. So, a brute force. So, the first is a brute force method. This is a straightforward method and it is based directly on the problem statements and the definitions of the concepts involved. This is actually not a systematic way, it is a brute force method. So, examples of those are computing a to the power of n, computing n factorial, multiplying two matrices. There is a method to which to do it and you have to do it in that method, searching for a key of a given value in a list. All these are example of brute force methods. Now, let us look at priority queue. This is a typical data structure and this priority queue is going to be used as an important data structure in different sorting algorithm, types of sorting algorithms. So, before we go further into that, let us discuss what is meant by a priority queue. If you look at the definition of a priority queue, a priority queue is an ADT. An ADT is an abstract data type supporting the following three operations. Normally, any data structure will support the following three operations. Add an element to the queue with an associated priority. So, add an element. So, that is what is the first operation that you do. Remove the element from the queue that has the highest priority and return it, or you can have another operation where you just want to look at the element with the highest priority and you do not want to remove it. So, this is like accessing that element. So, there are some sorting algorithms which use priority queue. So, in order to remember what is a priority queue where the dequeue operation always removes the element with the smallest key or remove min. As you remember, you can have priority queue based on remove min or remove max, it depends on what the application is, that is not a problem, but priority queue is basically a sorted queue. So, that is why we are going to use priority queue for two sorting algorithms. So, first let us look at selection sort. So, here what we are going to do is we are going to insert the elements in a priority queue implemented with an unsorted sequence. That is what we are going to do is we are going to have the elements, we are going to input the elements into an unsorted sequence and then we are going to remove one by one to create the sorted sequence. So, this is what we are doing in the selection sort. The same priority queue can be used for insertion sort. In insertion sort, we are going to do is we are going to insert the elements in a priority queue, but this priority queue has been implemented with a sorted sequence. So, what you do, you remove one by one to create the sorted sequence. So, what is the difference between selection sort and insertion sort? In selection sort, the previous one, what we have done is we have inserted the elements into an unsorted sequence and here we are inserted the elements into a sorted sequence. So, that is the basic difference. Please note these two sorting algorithms are using priority queue as a convenient data structure for implementation purposes. Next, let us go into that is so what we saw before was we saw the brute force, then we saw the use of priority queue for insertion and selection sorts, and now we are going to look at another concept of algorithm design in general, and here we are going to look at it from the sorting angle, but this divide and conquer method is typical of many algorithms and it is a specific concept that is defined in algorithmic design. So, an algorithm design technique, it divides a problem of size n into sub problems, then it tries to solve all the sub problems and then it merges and combines the solutions, that is the sub solutions got from the sub problems, and in that way it would have got the solution to the original problem. So, this method of doing things can result in very substantial improvements. Okay. Divide and conquer, as I already told you, is a method of algorithmic design that has created such efficient algorithm as merge sort. So, merge sort is a typical example of a divide and conquer technique. Again, just simplified way, what is a divide and conquer technique? Divide and conquer technique, you take the original problem, divide it into sub problems, find the solution for the sub problems and then you merge together the sub solutions. Now, the issue is how to divide the original problem into sub problems and how to merge the sub solutions that you get into the original solution, I mean solution to the original problem. Now, this divide and conquer technique is recursive in nature. What do you mean by this? You get a whole big problem, divide into sub problem, again you apply divide and conquer there, divide into further sub problem and so on till you get a trivial case, solve that, merge it together, go back and backtrack. So, that is what is meant by recursion. So, divide the problem into sub problems that are similar to the original but smaller in size, conquer the sub problems by solving them recursively. That is, if they are not small enough, divide them again. If they are small enough, just solve them in a straightforward manner, and then you combine the solutions to create the solution to the original problem. So, how is it recursive? You divide it into sub problem, this sub problem again called divide and conquer, that again you call divide and conquer and so on. So, the divide and conquer technique can be explained in this way. This is an example where the sub problem has been divided as n by 2. Suppose you have a problem of size say 50, you divide the problem into 2 problems of size 25, then you divide this into again of 12 and 13 maybe, then 12 into 6 and 6, then 6 into 3 and 3, then 3 into 1 and 2, and you have that 1 which is a trivial case, this 2 again you divide it 1 1, so you join it and so on. Here we are explaining it in terms of only this n can be anything. So, problem of size n divided into 2 sub problems of size n by 2 and size n by 2, and then you have a solution to the sub problem 1, you have a solution to the sub problem 2, and then you merge it together to get the solution to the original problem of size n. So, an example of this divide and conquer, please note this divide and conquer technique is not unique to sorting, it can be used in any algorithmic design. We are going to look at divide and conquer used for sorting. So, let us take the merge sort. If you remember, the time complexity of merge sort is of the order of n log n always, but then it requires of the order of n storage. Quicksort again is of the order of n log n average, and it requires and it is of the order of n to the power of 2 in the worst case, and in good in practice if it is greater than 30, and it requires approximately of the order of log n for storage purposes. So, that case quicksort is better. So, now let us go to a more generalized case of decrease and conquer. Here what we do is we reduce the problem instance to a smaller instance of the same problem, solve the smaller instance, there we were talking about sub problem, here we are talking about instance, extend the solution of the smaller instance to obtain solution to the original instance. Now, this can be implemented top down or bottom up. I hope you know what you mean by top down. You can start from the original big problem and come down, divide it and come down, or you can start from smaller problems, build it up and go to the original, and then that is called bottom up, the other one is top down. When you start with a major problem, keep dividing it, find the solution in the lower, after division, that is called top down. Here you solve a small problem and go up. This is also referred to as inductive or incremental approach. So, how do we break down the problem? Here we said that you have to reduce the problem to a smaller instance. How do you do that? You break the problem down by decreasing it by a constant, decreasing by a constant factor, or variable size decrease. You can even have variable size decrease. That is what makes this decrease and conquer into an interesting problem. It is not divide and conquer because we remove small bits and not halves. There we had n by 2. When I say divide and conquer, it is always n by 2. And run times are usually different. For divide and conquer, it is approximately 2 n by 2 plus order of n. For decrease and conquer, it is n minus 1, that is the solution to the previous problem plus 1. Here it is a solution to the n by 2, 2 times n by 2, you do 2 times n by 2. Here you understand the difference between these two. Here what you do is you divide this Tn problem into n by 2, so you have to do it twice. Here what you do is you reduce it to a problem n minus 1. How you define that n minus 1 we will see, and then plus 1. So, decrease and conquer technique can be explained this way. You have a problem of size n, you create a sub problem of size which is less than n, it can be any way lessened. So, we saw that there were 3 methods of decreasing it, by a constant factor, or a variable size decrease, and then find a solution to the sub problem, and then because you have found a solution to the sub problem, you try to apply the same n there and try to find the solution to the original problem. You do not do the merging here. So, there are 3 types of decrease and conquer. They are decrease by a constant, usually by 1. Example is insertion sort, graph traversal algorithms like depth first search and breadth first search, topological sorting, we will see this topological sorting as we go along, algorithms for generating permutation and subsets. All these are examples of this, these two are sorting algorithms, the others are not sorting algorithms, because as I already told you, this decrease and conquer is an algorithmic design technique, and here we are decreasing by a constant. Then you can also decrease by a constant factor, for example by half. So, binary search and bisection method is an example of this, or you can do exponentiation by squaring. This both are examples of decreasing by a constant factor. And you can also have variable size decrease depending upon the problem. You can keep on changing the size of your constant, and here you have an Euclid's algorithm, selection by partition and NIM like games. These are 3 examples of variable size decrease. We are not going to detail into these algorithms because it is not part of sorting, but this is just to tell you and complete that decrease and conquer is an example of algorithmic design. Now, let us look at what is the difference by considering this. So, we have looked at brute force, we have looked at divide and conquer, we have looked at decrease by 1, and we have looked at decrease by a constant factor. To actually bring out the difference, let us take this. You want to compute a to the power of n, okay. We are not taking a sorting problem, we just want to compute a to the power of n. So, in the case of brute force, you do a multiplied by this, multiplied by this, multiplied by this, and so on, so on, so forth. So, that is the brute force method. You do it one by one slowly. Next is the divide and conquer. Divide and conquer, you remember, you take this problem, divide it by half. So, suppose you have to calculate a to the power of 10, you calculate a to the power of 5 and a to the power of 5. To calculate a to the power of 5, again you multiply, do a to the power of 2 and a to the power of 3, or to the and then like that. So, that is the divide and conquer. Now, decrease and conquer is slightly different. What you do here is a to the power of n is nothing but a to the power of n minus 1 into a. Now, look at this, a is a trivial case. So, you have this. Now, how do you find n minus 1? You do a to the power of n minus 1 is nothing but a to the power of n minus 2 into a to the power of n minus 2 is, and so on, until you finally come to a. So, that is decrease by 1. Decrease by constant factor is a to the power of n is equal to a to the power of n by 2 the whole square. So, this is by a constant factor you are trying to decrease. So, this is a typical example how the problem of exponentiation is it is dealt with in an algorithm design sense by the brute force method, divide and conquer method, decrease by 1 method, and decrease by constant factor method. If you look at this, the brute force has been used in some sorting algorithms, each of this has been used in some or the other of the sorting algorithms, which is why we are describing this here. So, up to this point we have discussed only the approaches to algorithmic design and how those approaches are going to be used for the sorting techniques we will be discussing as we go along. And again, we are not going to look at the algorithm steps in detail. What we are going to look at is the approaches to the various sorting algorithms. Now, what we are going to look at is we are going to look at certain approaches to sorting algorithms. Okay. So, first let us look at selection sort. Now, selection sort is a sort algorithm obviously, and it is a comparison sort. So, let us look at the concept of how a selection sort algorithm works. So, what we do in a selection sort is we are not going to look at the algorithm steps in this lecture, we are only looking at the concepts of each of these algorithms, so that when we go later on and discuss the actual algorithm we will be able to understand it much better. So, find the minimum value in the list. So, look throughout the list and find the minimum value and then swap it up with the value in the first position. So, what is the first step you are doing? You are going from the beginning to the end of the list and then finding the smallest value, and then you are taking the first value and interchanging it with that minimum value, whatever position that minimum value is. Then you do the remainder of the list in the same way, but of course you will exclude the first value. So, suppose you had 5 numbers, you take the first number, you go through all the 5, find out which is the lowest and then exchange it. This is the most intuitive sort algorithm, it was designed that way also. Now let us go to the next one. So what is the selection sort? You select the minimum item, put it in the first position. Now select the second most minimum item, put it in the second position. Select the third most, put it in the third position, and so on till you reach, you have put all the elements in the correct positions. Now let us look at bubble sort. The algorithm gets the name from the way smaller elements bubble to the top, that is the head of the list, via the swaps. Because it only uses comparison to read elements, it is called a comparison sort. Due to its simplicity, the bubble sort is often used to introduce the concept of algorithms to in an introductory programming class to students. So, this is the bubble sort. Then you have insertion sort. So, we have seen now selection sort. What is the difference between selection sort and bubble sort? Bubble sort, what it does is it will keep on interchanging elements till the lowest element. So, what it will do is we saw one exchange sort in the last lecture, that was a typical example of a bubble sort. It is like a bubble coming up, that is the lowest will keep on, you keep on exchanging till the bubble, the lowest element bubbles to the top, that is the first position, and so on. In this we are doing only swap, local swap like, but in selection we are selecting the minimum element and putting it. Now let us look at insertion sort. In insertion sort, each iteration of the insertion sort removes an element from the input data and it inserts it in the correct position in the already sorted list until no more elements are left in the input. So here what happens is you have two containers. What you do is in the first container you remove an input data and put it in its proper place in the new one. Now when you are taking the second element, you have to put it, you have to exchange and put it in its proper place. So that is the insertion sort. The merge sort algorithm, what you do here is you sort the array, you cut the array into half and then you sort each of the halves and then merge the sorted halves. So this is dramatically faster than the selection, insertion and bubble sorts. Now you look there in the first three, we used basically the method of brute force. Here what we are using, we are using the divide and conquer method, where we divide the problem into two sub problems. You recursively sort each half and merge the two halves, and this is the divide and conquer strategy. Quicksort also uses a divide and conquer strategy, but here we select a pivot element in the list, which is usually the first element. We put the pivot element in the final position of the sorted element. Please note here, we are not looking for whatever that element is, you try to put it in its actual position it will have in the sorted list. All the elements less than or equal to the pivot element should be on the left of the list, and all the elements greater than the pivot should be on the right. That is a quick sort. Now you have shell sort. Shell sort is an extension of the insertion sort, but you have two observations. One is insertion sort is efficient if the input is almost sorted. Insertion sort is inefficient on average because it moves values just one position at a time. So we are going to modify this. So shell sort is similar, but instead of taking one step at a time, it takes bigger steps and it keeps on decreasing the size finally towards 1. In the end, shell sorts performs a regular insertion sort, but by then the array of data is guaranteed to be almost sorted. I will just repeat this. What we are doing is, we said that insertion sort is efficient if the input is almost sorted. So what the shell sort does is, it takes bigger steps and does an insertion sort till you come to a position where you are doing only with step 1, but by that time insertion sort, you do insertion sort, the input is almost sorted. So this way you are getting the efficiency. Next you have what is called a radix sort. A radix sort is a fast stable sorting algorithm which can be used to sort items that are identified by unique keys. What this unique keys means is, there is no duplicates allowed. Okay. Keys are assumed to be strings of the same length, this is okay, and every key is a string or a number, and the radix sort sorts these keys in some particular lexicographic like order. So we are assuming say characters, it could be names, or it could be localities, or it could be numbers, or whatever it is, it does it in a lexicographic like order. Now we will go into a very interesting sort which is called counting sort. The most of the sorts that we saw up to now were what is called as comparison sorts, which means that you compare two elements and do an exchange. You compare two elements and then put it in some place. Even for whatever sorts that we have seen up to now, let us take the first sort that we saw, selection sort, even there we had to find the minimum element. To find the minimum element, you had to compare it with all the other elements. Okay. So, that was the selection sort. In insertion sort, we again compared and put it in its proper place. In bubble sort also we did comparison, and merge, all those sorts we did comparison. Here is a different type of sort which is called non-comparison sort, that is called a counting sort. Now, what you are doing is you are sorts keys with values over a range, counts each number of occurrences of each key and calculate the number of keys which is lesser than each key, number of keys, okay, not the key element, which is less than each key, and it also counts the number of occurrences of each key. Place key in sorted location using the number of keys counted. If there are x keys less than y, please note, suppose you have x keys which are less than y, put y in the x position. Here is where in the previous cases where we have used comparison, in this case we are using the counting the number of keys which is less than y, and you are putting y in that x position, and you increment in position in which additional copies of y will be stored x times. Okay. So, suppose this is the original list. Okay. Now, for the count, what you do is you count how many times each of this has come. In this case all are unique. So, and what you are doing is you are assuming that it starts from 0, and 0 we always start, and it goes up to 8 because you have maximum values 7. So, what you do, 0 it does not happen at all, so 0, 1 it happens, so it is 0, does not happen, so 0, 2 1, 3 0, 4 1 because of this, 5 1 because of this, 6 0, 7 1 because of this, 8 1 because of this. Please note here that because all are unique, here you have only ones. Now, this is the next interesting part. Here also you are doing a count, here also you are doing a count. What you are doing? You are trying to find the number of keys that is less than 0 in this case, it is 0, 1 is 1, number of keys less than 1 is 0 because you do not have 1 or 0 here. 2 again, now if you look at 2, there are no keys which are less than 2, so again you put 0. Now you take 3, if you take 3, though 3 is not here, there is one key which is less than 3, that is this 2 which is here. Then you take 4, the number of keys less than 4 can be 3, 2, 1 or 0, you have only 2, so you put 1. Now you take 5, number of keys less than 5, 0, 1, 2, 3, 4, you find there are 2, so you put that there. 6 if you look, 1, 2, 3 keys are less, 7 again no 6, so 3 keys, 8 if you take 1, 2, 3, 4 all are less. So, this is the calculation of the number, please note you are doing counting. Now, let us take an example and see exactly how this works. So, what you do is this is the original array, okay, and you found that for 7 you have 3 elements which are less than 7. So, you put 7 in the third location, but you have to start with 0. So, 0, 1, 2, 3, 4. So, you put it in the third location. So, that is the first step. Now, after that you go to this step. Now, what you are going to do here is you find where the number of elements that are less than 2. So, 2 if you take, you have 0 elements that are less than 2. So, you put 2 in the 0th location. So, that finishes step number 2. Now, you go to step number 3. Now, step number 3 has got 8 here. Go to 8 and find how many elements are less than 8, which you have already calculated and put as 4. So, put 8 in the 4th location. The next step is, so the next step is you come here. Now, you have 5. So, find out 5, you have 2 elements that are less than 5. So, put 5 in the 2nd location. Next you come here, you have to find for 4. Now, if you look 4, 1, so put that in the 1st location, and so you have landed up with the sorted array. So, this is the count sort example. I will just explain it again. What you do is, the first step you take the elements, then you create an array which has the maximum lowest value 0 and maximum value which is greater than the maximum value there, that many elements. Then you find out, write a count of the number of elements that exist in the array given to you. Then you find out, fill the array with number of elements that are less than that particular element you are talking about, and that is what you get here. So, there are no elements less than 0, no elements less than 1, no elements less than 2, 1 element less than 3, 1 element less than 4, 2 elements less than 5, 3 elements less than 6, 3 elements less than 3 and 4 elements less than 8. That is your second step. Then you take 1 by 1, take 7, put it in the third position, take 2, put it in the fifth position, take 8, put it in the fourth position, take 5, put it in the second position, and take 4, put it in the first position. So, and you get the final sorted array. So, that is the counting methodology. We had comparison methodology and counting methodology. Now, one example of this counting method is the bucket sort. You divide key intervals into k equal size sub intervals and places elements from each sub interval into the bucket, and it sorts the bucket. It will use some other normal sorting algorithm for this, and then it merges the buckets together. So, that is the bucket sort, which is again a counting type algorithm. Now, let us look at, we had looked at 3 types or major categories, that is the comparison type of algorithms, the counting type of algorithms, and the external sorting type of algorithms. So, the topological sorting is a typical external type of algorithm. It is used to order a directed acyclic graph DAG. List the vertices of a graph, this is the problem. List the vertices of a graph in such an order that every edge in the graph, the vertex where the edge starts is listed before the vertex where the edge ends. So, you must have that is the order you want. The order you are defining is the vertex where the edge starts should come before the vertex where the edge ends. So, that is the topological sorting problem. So, in graph theory, a topological sort or topological ordering of a DAG is a linear ordering of the nodes in which each node comes before all nodes to which it has outbound edges. So, every DAG will have one or more topological sorts. This is a definition of topological sorting from Wikipedia. Now, let us take an example. This is how the topological sort works. Find a node for which you have no input edges or incoming edges and remove it. So, here C1, C2, C3, sorry, C1 does not have any incoming, C2 does not have, all the rest have. So, you could have removed C1 or C2, we choose to delete C1, this is what happens. Now, this does not have any incoming edge, this has, this has. So, the next choice is you remove C2, so you remove C2. Next you have this has incoming, this has incoming, C3 does not have, so remove C3. Now, C4 does not have, remove C4, and finally you delete C5. So, the solution is C1, C2, C3, C4, C5. Illustration of the source removal algorithm for the topological sorting problem is what we have seen here. And on each iteration what did we do? We removed a vertex which had no incoming edges and along with its edges, okay, that is what we did. So, finally, to summarize what we have spoken about in this lecture, we looked at the brute force method, we looked at the priority queue data structure used for sorting. We used it for 2 types of sorting, selection sort and insertion sort. Then we looked at the concepts of divide and conquer and decrease and conquer, and then explained the concepts of selection sort, bubble sort, insertion sort, merge sort, quick sort, shell sort, radix sort. Remember, we have not gone into any steps, we have just explained the concepts. Then we looked at the concept of counting sort with an example, and then we discussed bucket sort, which was an example of counting sort, and topological sorting, which is an example of external sorting. Now, I want you to do the following problems to understand. I want to differentiate between comparison sort and non-comparison sort with an example from each, and then using this counting sort I want you to arrange this particular array using counting sort. Obviously, this should go from 0 to 10 and then you have to do the work. I want you to simulate this topological sorting for the following graph. Remember, there is no one topological sorting problem, answer, it need not be unique, depends on which node. Suppose you have 2 nodes with no incoming edges, it depends on which node you want to take. So, try for this. So, this is what we have discussed in this lecture. Thank you.